Today I'm going to share you our experience of using proof techniques to build kernel components with very high correctness assurance. So this is work we have been doing at MIT and University of Washington. So actually currently a lot of modern operating systems allow users to specify code, and they actually download code into the kernel for execution. So here's a list of kernel interpreters. Actually, you can see this Seccomp is a sandboxing interpreter, and this will be focus of this talk. And you can see the kernel actually running a lot of interpreters. And because the kernel is actually downloading code into the kernel for execution, so if the code itself is malicious, you have to be careful. And because the system is making decisions based on the result from interpreter, so any bugs in there would be a big deal. So you have to be very careful. But unfortunately, there are a lot of bugs being found recently in those interpreters. So here's, we did a case study of those bugs. So you can see you can find basically bugs everywhere in kernel, in user space, and in the boundary between kernel and user. And you can see a bunch of familiar friends like buffer flows forever, and also control flow errors, and then incorrect correctness bugs, and all kinds of privacy issues. And some of those bugs have very serious security consequences, like you can do actually code injection into the kernel. So one question we want to ask is, how can we get rid of all of those bugs at once? So one promising technique is theorem proving. So as shown by pioneer work such as CSAIL 4 and CompCert, so we can see they have used proof techniques to build microkernel or C compiler with very high assurance of correctness. So this talk, I'll describe you Jitk. It's also using proof techniques. We're going to show you how we do it to build an interpreter for running untrusted user code in kernel. It can be used as a drop-in replacement of the Linux kernel Seccomp subsystem, and we build it using the Coq proof assistant and CompCert. So what is theorem proving? So let me give you a high-level overview. So to do theorem proving, you need to do three things. You need a very nice, clean specification that describes what the system should be doing. And then you can have a fancy, crazy implementation that could optimize for performance. It could be very complicated. Then you write proof to show that the implementation meets the specification. So I want to emphasize 3 points. So first, the proof is machine checkable. So you can use Cog, other provers to check those proof. So you have to make sure the proof actually is correct. And then the proof guarantees that if the specification is correct, then the implementation must be correct. So that's a good part you can get from proof. And then I want to make a point here is specification should be simpler than implementation. Otherwise, there's no point of doing proof. So there are several challenges of applying these proof techniques to build a kernel component like Jitk does. So first question is, what's the specification? What do you mean by a correct Seccomp subsystem? And even we have these high-level ideas of what the system should behave, how do we translate those high-level intuitions into formal proofs? And the third, how do we get running code? So in the rest of the talk, I'll focus on 3 parts. How do we write down specifications that capture system properties? How do we actually translate them into formal theorems? And how we integrate GK with the Linux kernel. So let me give you some background of this Seccomp subsystem in Linux. So this mechanism allows applications to reduce the attack interface. In this case, the syscall interface. It works in 3 steps. So in the first step, the application submits a Berkeley packet filter, a BPF program to kernel. So one example of this, such a BPF filter could be, oh look, if the syscall is open, then fail the system call with some error code. Then you can see now the application cannot open new files at all, even if it's compromised or controlled by an adversary. And the kernel enforces this in 2 steps. First, the kernel actually invokes an interpreter to execute the filter against each system call. And based on the result, the kernel then decides whether to allow or deny this system. So here's a concrete example of Seccomp BPF code used in OpenSSH. So you can see first it loads the system call number, and then it checks, okay, if it's open, then jump to some place, and then it checks if it's get time of day, and then it's okay. And if it's not processed, then just kill the current process. And this particular component is very interesting because it's security critical. It's widely used by a lot of applications, and also it's on the critical performance path, so you have to do it fast. And it's not trivial to do right. We have found a lot of bugs in it, and also it's a general design which you can find in a lot of OS kernels. So now let's take a step back and think actually what's the specification here, like what a correct Seccomp should do. So the high-level goal here is to enforce user-specified syscall policies in kernel. So what does that mean? So let me break it down for you. So first, it means what the kernel executes should be what the user specifies. And that means for the kernel, when it accepts a BPF program, the x86 instruction the process is running should be the same as the BPF program. And second, the BPF program should be correctly transferred from user space to kernel. And third, in the user space, when you actually write down your policies as BPF programs, the BPF programs, the input itself should be correct. The other category of properties is about non-interference with the kernel. So you actually are doing this subsystem. You should not crash your kernel. You should not cause infinite loops, and you should not overwrite the kernel stack. So in this talk, I'll focus on the first 3 properties and show you how we actually formalize those properties and we do proofs. So the first part is how to actually execute BPF program in kernel. So we do a just-in-time, a JIT compiler that translates BPF to x86 code and run it in the kernel. And building JIT actually is hard. So here is one actual example in Linux. So this is a JIT code. You can see it emits a bunch of crazy opcodes. And where's the bug? Actually, there's a very serious bug. This is 6. It's wrong. It should be 5 because it's jump plus 4 bytes offset. And actually can exploit this bug and to inject code into the kernel. So we want to avoid that kind of bugs. And the goal here is to say the x86 code output by Jitk preserves the behavior of the input BPF. So the implication is if we can achieve that goal, then the output x86 cannot have a large class of bugs. It cannot have buffer flows, cannot have control flows, because those bugs do not exist in BPF. So how do we do it? The high-level idea is to first model BPF and x86 as 2-state machines. So we read manuals and original papers of BPF. We write down the specifications with our understanding. So for BPF, the state consists of registers, fixed as memory, the input, and the program counter. And every BPF instruction serves as a state transition from one BPF state to another. So for x86, you can imagine it's even simpler, right? So just in a similar way, also a state machine. But we don't want to do it, so we actually borrow it from CompCert. And the actual theorem we want to prove is called the backward simulation. That says if our JIT succeeds, then every state transition in the output x86 corresponds to some high-level state transitions in BPF. Then we are done. So how do we prove this? A strawman approach would be, okay, let's just write one translator from BPF to x86 and prove it. And this is hard for 2 reasons. One is this is actually, you want to say the output x86 corresponds to some input, and that's actually the inverse direction of the translation function. So it's very hard to do the proof. And the second is there's a big semantic gap between BPF and x86. So we address the two challenges with two techniques. So we first use forward simulation. First, we prove a forward simulation, which is way easier to prove, and then convert it to the backward simulation. So the idea is to say we prove for every state in the high-level BPF, in this case, actually corresponds to some low-level transitions. So that's the same as a translator. Then that's way easier to prove. And the second trick is we can add intermediate languages between BPF and x86 to bridge a gap. So here we choose this language called C minor, which is from CompCert. So it's basically like a type-less C. So it's a simpler version of C. And we choose that as a detour. And we prove BPF to C minor. And then we combine it, and we reuse the existing infrastructure in CompCert, which proves C minor to x86. Then we get this nice property of correctness of BPF to x86. So let me, this is our new hierarchy here. So let me move to a second example. So the goal here is we know application submits BPF code to the kernel in the form of bytecode, and the kernel actually has a parser that decodes bytecode back to the abstract syntax tree, like the actual data structures in kernel and for execution, and there were bugs found in this case. So how do we ensure this BPF is correctly decoded by the kernel? So one strong approach would be to similarly do a state machine simulation as we just did before. So we could write a spec, also like a state machine for the bytecode BPF, and then we could show a simulation between bytecode BPF and the actual abstract BPF. But the challenge here is that the specification for bytecode BPF is really hard. So you can imagine for each byte, you have to define some state transition, and that's basically what the code does. So the specification would be as complex as implementation, and there's no point of doing that kind of proof. So our approach is to first, we write two implementations, decode and encode, and we choose a much simpler spec. So we just show equivalence of the two functions. So whenever you encode a filter into some bytes, and then you decode it, and the result is original filter, and we believe this actually gives some assurance of the correctness of decode. And of course, the trade-off here is we could have sort of consistent bugs. So if encode and decode and make the same kind of mistakes, then this theorem actually wouldn't be able to catch it. So that means the decode could be behave differently from the existing BPF in the kernel. Yeah. The third thing I want to talk about is in user space. So look at this input BPF in OpenSSH. So how can you convince yourself that this actually is correct? This is not so trivial. You can see this has a lot of control flows, a lot of jumps, a lot of conditions, and it's hard to convince ourselves this is the correct BPF that captures the right policies. And the second question is the BPF spec. How do we know the spec we wrote down actually is correct? So we address this problem by defining a new higher level domain-specific language for writing system called policies, so this SCPL. So you can see this language actually has the same functionality as the BPF program I just showed, but it's way simpler and cleaner. And we believe in this case it's much more unlikely for programmers to make mistakes in this part. Another interesting thing I want to emphasize is here we build an extra level above BPF, so programmers can choose to use our SCPL instead of directly writing BPF. And then you have a nice property about this also end-to-end correctness. So in this case, you don't even have to trust the BPF spec, and you have a higher confidence that the BPF spec is correct. So let me sum up the approaches we used in the JK. So one useful technique is state machine simulation. We do this from BPF to x86 and from higher level SCPL to BPF. There are a lot of interesting tricks you can use. You could add extra levels between the two to bridge the semantic gap. You can convert simulation to backward simulation for easier proof. And if you want to get more confidence about your correctness of your specification, you can build up the abstraction stack. And to get the equivalence of the kernel data passing, so we choose equivalence instead of actual state machine. So we think this trade-off is good because it offers a simpler spec. So now let's move to some implementation details. So here's the development flow of Jitk. Developers write those shaded boxes. So you can say you need to write the specification, the proof, and implementation, and you send all of these to a clock proof checker, and the checker says, okay, then you know the implementation should meet the specification. And after that, you can extract code from implementation using a clock code extractor, and then you would have a OCaml program. And then you can use OCaml compiler to compile that into a native executable. So you could have those BPF to x86 translators and also SAPL translators. So in the middle, you might need to write some IO stub code, which is very simple. And here's the actual design here. So you can see now programmers can optionally choose to use SAPL. So they can write high-level SAPL rules, use a compiler to generate the BPF bytecode, or they can just use BPF as before. And then there's a BPF Jitk in kernel that translates the BPF bytecode into x86. And later on, the kernel will invoke that generated code for execution to check those system calls. So here we made two modifications to the kernel. We first modified the kernel to invoke this translator. Because this translator includes OCaml runtime and the GNU assembler, so for now in our prototype, we just invoke a user space helper as a trusted process, but you could also port that entire thing into kernel. Another thing we did was to modify kernel just to invoke the generated code. Now, I want to have a little bit of discussion about the theorems. Like, what do we get from those theorems? So we manually inspect those existing bugs, and we so we believe that the theorems can stop those kind of classes of bugs, like those control flow bugs or the kinds of memory bugs and those correctness arithmetic bugs that should all be gone because of our correctness theorems. And similarly, we have a guarantee from the kernel user boundary bugs and user space bugs, so those bugs should not happen. So I want to discuss a few limitations, like what the theorems cannot prevent from. So the first, the theorem is about if our JIT accepts the input, then the result be correct. So that means our JIT could reject some legit input, but we believe this is not a security issue, so it's fine. We cannot prevent side channel attacks because it's not modeled in the specification. If there's a bug in the specification, like in those SAPL, BPF, or x86, there's nothing we can do about it. And also we share the same TCB as CompCert, so if there's a bug in clock, the OCaml runtime, or the GNU assembler, then we have no guarantee about that. And also we have nothing to say about bugs in other parts of the kernel. So I know this is OSDI, so I'm going to show some numbers to make you happy. So I'm going to show you how much effort does it take to build this component, what's the end-to-end performance, and how about the code quality generated from Jitk. So here's lines of code breakdown by component. So you can see for specification and implementation, it's only a few hundred lines of code. The proof is the largest part. It has over 2,000 lines of code. And the modification to other parts are minimal. So overall, it's a little bit over 3,000 lines of code. And we have used a lot of like components from CompCert, which doesn't show up here. So we believe the effort here is moderate. So here are some end-to-end performance numbers. So the setup is we are running OpenSSH on Linux x86. So for stock Linux, because it doesn't have an x86 32-bit JIT, so it's actually running in interpreter mode. And for our case, Jitk is actually running in the JIT mode. And here's our two kinds of overhead numbers. The first is there is a one-time compilation from BPF to x86 overhead. It's 20 seconds per connection per session. So that doesn't happen later. So the most important overhead here is the per syscall. That's the most critical number, the per syscall overhead. And you can see here this time measured in milliseconds. So baseline is the Seccomp subsystem is disabled. And you can see our performance is pretty good. And to understand how this happens, so we also inspected the assembly code generated by Jitk. So here is, we chose a bunch of BPF programs connected from a lot of applications. And then we run Jitk and existing kernel JITs, and we compile the code size. So you can see Jitk produce pretty good code, and oftentimes actually better than existing JITs. And we inspected those code and found out the reason is because existing BPF JITs are in kernel, so it's very hard to write complex optimizations in kernel. And Jitk can leverage optimizations from CompCert, and those optimizations are proved to be correct. There have been, I want to discuss some related work. So theorem proving work such as CSAIL and CompCert, this pioneer work shows us a promise of theorem proving, and also this talk shows you how to use theorem proving to build a trusted kernel component to run user-specified code. There are model checking and testing techniques that are very useful for finding bugs, but they cannot guarantee bug-free under a few assumptions. Techniques such as microkernel, software fault isolation, or type-safe languages, they are focused on memory safety properties. So they can prevent a lot of bugs, but they cannot deal with correctness bugs as we can. So to sum up, Jitk is trustworthy component that can actually run trusted code in kernel with theorem proving techniques. It provides very strong correctness guarantee. It has pretty good performance, and we hope the approaches will be useful for proving systems properties. Thank you.
Hi, I'm Rich Draves from Microsoft. I was curious how your system would compare to an old idea of proof-carrying code, where instead of having a JIT logically in the kernel, if you could, just have arbitrary code that carries a proof with it.
Thanks. So the question was, how do we compare like proof-carrying code and this Jitk? So the original, so I want to make 2 points. So the first proof-carrying code was in OSDI 1996. So that paper basically focused on memory safety properties. Like you don't have arbitrary jumps in the XD6 code or the alpha DAG code. Then actually it doesn't really deal with correctness bugs. In principle, you could, but actually they focus on memory safety bugs. A second point is this flavor of this thing is actually, the term is difference between correctness, this translation validation and the verification of this translation. So what it means is for each instance of an input program, proof-carrying code actually generates one proof. And in this case, Jitk, it just generates proof for all instances. So that's a key difference. I hope that clears up something.
So could the proof-carrying code approach be extended for these other properties that you care about?
Maybe. We don't really have experience with that. The papers we saw actually mostly focus on memory safety bugs. Yeah.
Okay.
Hello, Malte Schwarzkopf from University of Cambridge. Can you quickly go back to the performance slide with the persistent overhead? I just have a question on that. You say the overhead is in milliseconds and the numbers are in the hundreds. Even your base number is like 450. Is that really in milliseconds, or am I misunderstanding the experiment here? 450 milliseconds per system call seems rather large.
We just run several hundred million times for the get time of day.
Oh, okay. This is over multiple runs.
Yeah.
Okay. a different, more conceptual question. So you said that you now have the OCaml runtime and the GNU assembler in your TCB. One of the arguments early on in the talk was building JITs is hard, and people are going to make mistakes. I would assert that building GNU assemblers and OCaml runtimes is hard, and people are going to make mistakes. So how do you balance that trade-off? Do you think these things are more widely used and therefore going to be more stable, or can you prove them correct, or something like that?
Yeah, I think that's a great question. So the question was like, OCaml runtime itself is not that small. Like, how do we know this part is correct, right? So I think this basically the same as when you use any theorem proving techniques, so you would have this problem because you are running this prover calc, which actually is built on top of OCaml runtime, which is compiled by GCC, which is running on a stock Linux kernel. So conceptually, the entire trust computing base includes OCaml runtime, includes GCC, includes Linux kernel entirely. So, actually, I think the key point here is there are so many levels of interactions. So you have a confidence, or it's mostly unlikely this could happen to become like interesting attacks, as we see earlier in the case.
Yeah, that makes sense. Thanks.
Thanks.
Hello, I'm Volodymyr Kuznetsov from EPFL. So I have a follow-up question to this one. It's more high level. So I think it is amazing work, and it is good that we are moving in the direction of proofs. But before we can prove everything, it's a long while. So we'll always have to run some proven code alongside with something that is untrusted. So can you think about any ways to use some isolation, some hardware features, anything, to still be able to prove properties about the entire system that includes both untrusted and proven code?
Yeah, thanks. So the question was, so in the current state of art, so we have trusted code and untrusted code and proof code.
Yeah.
How do we actually proceed?
Exactly.
Yeah. So I think there are a bunch of interesting techniques or work going on. So I remember earlier this year, there was a PODI paper from University of California at San Diego. So they actually built a small kernel-like thing. So that part is trusted. And they are running browsers and OpenSSH on top of that. So what they prove is like each tab, like tabs cannot interfere with each other. But each tab inside itself is untrusted. So you have a high-level security probability guarantee, but you don't really have a full like functional correctness as we have shown. But I think that's one step you could adopt.
Okay, thank you.
Thank you.
Speaker.